Okay, the next question is all about dimensional analysis. It's conversions. Okay, so I'm going to give you these relationships, but you do need to be able to use them. So 1.8 atmospheres into 8.4 atmospheres into torr. So remember, mmHg is also torr. They're the same thing. So I have 760 torr for 1 atmosphere. I choose to put atmospheres on the bottom so that it will cancel. And so I expect my answer to be over 760 since, I'm multiplying 760 times 1.84. So this is what I get from the calculator. I only have 3 sig figs, so I have to stop there. So we're going to go... Now this one's awkward, because if I have to round, right? So this 8 has to get rounded. So I think what I'll do is put it into scientific notation. That way I can keep the right number of digits. So it's going to be to the 3rd torr. Okay. So this relationship is provided to you for the exams, but you need to know how to use it. The same thing here. So 0.91 torr, or atmospheres into torr. This should be less than 760 this time, because we're starting off with less than 1 atmosphere. The only difference here is understanding that these two words mean the same thing. So we get 691.6. I only have 2 significant figures, so I guess I'll just write 690. 2 because of the atmospheres here. The number of significant figures in your conversion factor does not matter. That's a definition. We say that there's exactly 760 torr in an atmosphere, so that is not going to limit us. It's just the data, the number that we're provided with in the beginning. So same conversion factor here, we just have to flip it over, right? So it's still the same relationship, but now I want to cancel torr. So we put in 735 divided by 760 because that 760 is on the bottom. And we get 0.967 ATM. Okay. The last one is an atmospheres to pascals. Now, so atmospheres, our little conversion factors say that there's 101.325 kilopascals per atmosphere. And then I need to remove the kilo, so it's going to be 1,000 pascals for 1 kPa. So we have multiple steps here. So get rid of the kPa there, get rid of the atmospheres there, and we end up with pascals. Okay, so these are all being multiplied together, and our answer from the calculator is 142,868.25. So quite a big number. I only have 3 significant digits to begin with, so that means I have to write, oops, I didn't mean to write in yellow. Let's see. I have to write 143,000, or 1.43 times 10 to the 5th. Either way. And this is going to be pascals. Okay. Okay, so the next question is an ideal gas equation. Well, it could be the ideal gas law, or it could be one of either Charles' law or Boyle's law. Okay, so we have a sample of gas has a volume of 4.6 liters, so that's a volume. At 750 torr, torr is a pressure, so I'm going to write 755 torr. The pressure of the gas decreases. Oh, okay, so we have an initial pressure and a final pressure, and it's going down. When pressure goes down, I expect the volume to go down also. So like if it's less pressure, it pushes on the container less, so it's going to shrink. So my answer should be less than what I'm starting with there. Okay. And it wants to know the final volume of gas. Okay, so this is really a Boyle's Law question because we're relating pressure and temperature. Or sorry, pressure and volume. Temperature is constant. I know that it's constant because it doesn't tell me that it's changing, so we're assuming that it's going to be the same throughout the experiment. Boyle's Law means the pressure and the volume are like proportional. No, wait, they're not proportional. Sorry, that's wrong. I was remembering our graph. So our graph shows pressure on one side and the inverse of volume, and they're proportional this way. So it's inversely proportional. Okay, so that means the equation for Boyle's Law is going to be, if I multiply the pressure and the volume together, initially it's going to equal pressure and volume after something has changed. Whether the volume changes or the pressure changes, I can calculate it either way. So this is one way to do this problem. So we can take pressure 1. I don't even need to convert because the torr are going to cancel, so it doesn't matter. So 755 torr times the initial volume equals the new pressure times the volume I'm looking for. Okay, and so we end up, dividing both sides by 720 torr, and so that's what I meant about torr canceling. And this way we get V2 on its own. Okay, so the answer is going to be in liters, which is perfect. That's what I want. So V2 is going to be 4.8236. So I'm just going to keep 2 sig figs because that's what I had from my original volume. So it's 4.8 liters. So pressure went down, volume went up. That's what we expect from our experience of Boyle's Law. They are opposite. If the pressure decreases, that means that the volume had to have gotten bigger, giving more space for the molecules to run around. Okay. There's another way to solve this. Actually, there's several ways to solve this, but another method that you might use would use the ideal gas law. Okay, so this is the fastest way to do it, at least I think it is. But you could also plug your information in. You have to assume some temperature, so I'm just going to assume 273 Kelvin because it's easy, it's 0 Celsius. It doesn't matter what you pick because the temperature is the same throughout it, so we're going to kind of cancel that out later. Okay, so if I want to find the volume with the ideal gas law, I first have to know the moles in our starting situation. So initially I'm going to find moles. All right, and so pressure, I'm going to have to convert these because my R is this. Okay, so the first step is conversions, then finding moles, and then plugging moles into another version of the ideal gas law where I'm solving for V. Okay. So for both of these, I'm going to multiply by the conversion factor here. So P1, we end up with almost 1 atmosphere. It's 0.993. For P1. P2 is 720 divided by 760. We get 0.947 ATM. Okay. So I'm just going to plug it in and solve for moles, all right? And I like to rearrange first. So that's what we get. So N is pressure, our initial pressure, which is 0.993, times the volume, divided by our constant. I know you're tempted to not write these units, but you'll regret it if you do, because you'll mess it up. All right, and then times temperature on the bottom, and it's got to be in Kelvin. That's a common error. I just picked a temperature, so it was in Kelvin automatically, but usually they're going to give it to you, in Celsius. So watch out for that. All right, we end up with inverse moles, 1 over moles on the bottom, which means it's actually just moles, which is perfect. And so the math here, So on the top I get 4.5678. There's no unit because they all canceled. And then divided by 22.4 on the bottom. And so from that we find that there's 0.204 moles of gas. Okay, so now that I know how many moles of gas is there, I'm going to clear some space here for myself. It's 0.204. Oops, took the wrong part. I'm going to use the ideal gas equation all over again, but this time we're solving for volume at the new pressure. Okay, so it's going to be volume equals nRT over P. The moles I know from the last part. R is the same. I'm just going to write R because I'm going to run out of room, but you should write it all down on paper. And our temperature is still 273. Okay. And then the pressure on the bottom is going to be our lower pressure, which we found at 0.947 atmospheres. So here's liters atmosphere per mole K is our unit right here. So the K's cancel, the moles cancel, the atmospheres cancel, and I get liters. So I've set that problem up correctly. Okay, so we're going to enter 0.204 times 0.08206 times 273, and then all that divided by 0.947. And we get 4.82 liters, which is, I think, exactly what we got before. Oh, but we only have 2 sig figs, so I guess it's just 4.8 liters. Okay, so 2 ways to solve the same problem. Okay, so there's a lot of ways to approach this problem. The one I think is the most straightforward is to realize that the total pressure is equal to all of the different components combined, right? So the pressure from nitrogen, pressure from oxygen, pressure from argon, pressure from carbon dioxide. Okay. So it equals the total moles times RT divided by V. So I don't need to solve each of those individually to begin with. That's not really the question. The question's asking for moles of air, so it's easier to get the total moles of gas this way. So our P total is 1 atmosphere. We can actually just rearrange this. Let's back up a little bit. So if I wanted to find N total, I would multiply by V, divide by RT. Okay. So my total pressure will be 1 atmosphere times the total volume, which is a big volume. So it's in scientific notation. I know that looks like 106. That's just my iPad. It doesn't read font very correctly. And then R on the bottom. And T on the bottom also. So our temperature is 20 degrees. So the T has to be 20 plus 273, which is 2. Whoa, that's a crazy 3. Okay, it's 293. Always remember to convert to Kelvin when you're doing gas problems. Let's see, atmospheres cancels, liters cancels. I get 1 over moles, which is on the bottom, so that's moles. Okay. Okay, so because I have such a huge volume, I'm expecting this to be a really large number, so don't be shocked when your calculator tells you that it's a lot. That's a big volume, so it's going to have to be a lot of moles of gas. So I punch it in the calculator and it says 116455. I have 3 sig figs, so I'm just going to write 116 and then 3 zeros. Moles. There are other ways to solve this. Some of them are longer, but this, I think, is the most straightforward way to do it. If you got basically the same answer, don't sweat it. You had the right process. Okay.